The destructive power of quantum computers. Deciphering the secrets of the universe. What if all your digital information is disabled? In an instant, a world where decryption that would take millions of years is possible in just a few minutes. Quantum computers have that devastating potential. The theory that ordinary computers can decipher the difficulties that cannot be solved even if they mobilize all the atoms in the world with only hundreds of qubits. But the revolution that this technology will create goes beyond mere decryption. This innovative technology could be the key to deciphering even the deepest mysteries about the birth of stars and the origin of the universe that we still haven't solved. From now on, let's take a deep look at the secrets of the universe that this technology will unlock, along with innovations that will shake up the foundations of existing computing and the core principles of quantum computers. The basis for the operation of quantum computers lies in quantum mechanics, which is different from the laws of physics in the world we live in. Unlike when the bit, which is the information unit of a regular computer, has only one or two values, the basic unit of a quantum computer, qubit, has a superposition state that can be 0 and 1 at the same time. It's like a coin going round and round without collapsing. Thanks to this superposition state, quantum computers can handle huge-scale computations that are impossible with conventional computers at a very high speed. A normal computer can do 1024 calculations, and a quantum computer can do it in a single state. In addition to this, an entanglement state in which several qubits are interwoven with each other is added. This entanglement is a property in which the state of one qubit is determined immediately when the state of the other qubit is determined, maximizing computational efficiency and being used in key techniques such as quantum error correction. This overlap and entanglement is the key to quantum computers' ability to outperform supercomputers. The area where the capabilities of quantum computers are most threatening is decryption. Estimated that it will take about 1 million years to solve a 2000-bit password on a supercomputer. However, quantum computers can theoretically handle this prime factorization very efficiently. If developed properly, it is predicted that this code can be decrypted in minutes or hours. It is like a devastating window of sleep that will shake the foundations of financial systems, state secrets, and privacy around the world. In response, the scientific community is preparing a new shield: the study of quantum resistance cryptography. It is a method of creating a password using a new mathematical problem that is difficult to solve even with a quantum computer. US state agencies recommend replacing all passwords with quantum-resistant ones in the next 5 to 10 years, underscoring the urgency of developing the technology. The use of quantum computers extends beyond decryption to the most fundamental questions of mankind: the origin of the universe and the secret of life. How stars are born and die and how they harbor that tremendous heat is determined by their mass, chemical composition, and evolutionary stages. The heavier the star's mass, the hotter the internal temperature must be to counter gravity. In addition, when it expands like a red giant, the surface temperature drops, and when it contracts like a white dwarf, it heats up to hundreds of thousands of degrees. All of this is done through fusion reactions governed by quantum mechanics. In particular, the recent discovery by James Webb Space Telescope, Little Red Spot, poses a big mystery. This red light celestial body resembles a theoretical black hole star that contains a black hole 100,000 times the mass of the sun at its center, and is covered with thick clouds of hydrogen to emit light. These celestial bodies are found only in the past 12 billion years ago, and it is estimated that they may be fetal stages of giant galaxies today. It is impossible to simulate phenomena dominated by quantum mechanics, such as the origin of the universe or complex interactions of microorganisms, with ordinary computers. Only quantum computers can process this vast amount of data and mimic complex quantum phenomena, revealing the secrets of the universe we never even imagined. Quantum computers are not yet in their complete stage, and they are currently in the Chunchu warring states era, where several systems compete. In particular, systems using superconducting qubits have to overcome enormous challenges to function properly. It's cryogenic cooling. These qubits require temperatures lower than those of outer space, which is close to absolute zero. The chandelier-like complex structures we often see in pictures are coolers to maintain cryogenic temperatures, and the chips are mounted on the coldest parts of them. It maintains this temperature by mixing helium-3 and helium-4 to reduce the pressure. Quantum computers exist in specific centers like supercomputers rather than in general homes for the time being, and are likely to develop into a form that users can access and utilize remotely. The challenges the technology must overcome are clear: increasing the number of stable qubits and pushing beyond the technical limits of maintaining cryogenic temperatures. Quantum computers have the potential to fundamentally change the way humans understand the universe and reality surrounding themselves, beyond just technological advances. The main reason why quantum computers are currently not widely used in real life is the fundamental limitations and instability of the technology. Quantum computers are still in their early stages of development, especially experiencing great difficulties in reliably controlling and expanding qubits, a key component of processing information. Qubit instability and error rate. Quantum computers process information in superposition and entanglement states. These two core principles give enormous parallel processing power, but they are extremely difficult to maintain. Extremely sensitive environments. Qubits are easily interfered with even the smallest noise, heat, electromagnetic waves, etc., around them, resulting in decoherence, in which the quantum state is broken. High error rate. Current quantum computers have a very high error rate compared to regular computers. Because the results of the calculations are probabilistic, the same calculations must be repeated numerous times and processed statistically to increase accuracy. Limitations of technological scalability. While the performance of quantum computers increases exponentially with the number of qubits, increasing the number of qubits is extremely challenging. Number of qubits. It is estimated that thousands of stable logical qubits are needed to break the current RSA cipher through prime factorization. The number of qubits remains in the dozens to hundreds range, which has not yet reached the specification to break the cipher. Limiting the available algorithms. Only in certain areas. Software shortage.